want to take a look and see what deformation is. Same thing with the convergence of the frontogenesis that we saw in a couple of slides ago. Basically, you have a certain temperature gradient here. You have converging there. Basically, the end state is going to be that your isotherms are more packed together, and that's your frontogenesis, and creating a front in there because you're increasing the temperature gradient. So like say in a real world, you have say a 700 millibar low, and the flow around that is like this, and then you have basically your wind flow and it turns a little bit. And there's an area right here, say we have the, show the deformation again, where you have your deformation zone where the air parcels are actually splitting apart here. That's kind of what's happening here. Your wind is trying to blow this way around the upper low, but at the same time around that to the east is blowing this way. So where would you have your deformation zone? Your deformation zone is gone. So your deformation zone is going to end up being here because you're stretching, say this is a box or a circle, you end up stretching that, so you're actually tightening up that zone. As long as you have a temperature gradient for the deformation to work on, you'll always have frontogenesis. So let's take a look at a conceptual model here. A lot of times you'll have your upper low, your surface low down to the southeast of the upper low, and your deformation will be in a pretty large area. Then you'll have your frontogenesis band sometimes to the northeast of the surface low. Those bands are usually transitory, so you won't get too much snowfall up here, but the ones that we want to concentrate on are the bands that form back here to the northwest of the upper low. Those are the ones that are more exciting. There's kind of a checklist that you want to look at, basically for heavy snow banding. You don't want dry air advection near the surface. You don't want to dry the surface out. You basically want to be saturated in the column. You want your snow microphysics to be good. You don't want you want your cloud top temp less than -9°C, and you need an area of frontogenesis in your deformation zone. We'll kind of show that. What? You want presence of instability, which can come in the form of CSI or just regular convective instability. And like we showed last year, you want snow growth in your -12 to -18°C layer. Like, and you can visualize that through BuffKit. So here's Will let me borrow this thing.
Yeah, it's from Weather Underground.
So why do you get this band? Why do you get this band like to form right in the middle of the? Why do you get this band to form right in the middle of the area of precip? Demons. Keep it up. So let's take a look at the GFS forecast and AWIPS. This is 0Z Sunday, February 12th. So about 6 to 9 hours before the band really started to form in New York City. Your green is your 700 millibar height. Your wind barbs at 700 are in yellow, and your temperature is the dashed blue. So you have a pretty decent temperature gradient here associated with the warm air advection. You're crossing your isobars. So you're going to have warm air advection snows in here, but your temperature gradient isn't really that tight yet. But actually, if you look and think about what we saw in the deformation slide, see how the winds are coming around to the northeast, then they're trying to turn to the northwest here, and then the northeast up here. So not only that, you have pretty good speed convergence, 50 knots, 40 knots, and then just to the north of this gradient, you have 10 knots of wind. So your air parcels are all smashing together in this area. So I'll overlay deformation here. It's not too strong, it's the low end of the scale, but you can see that you do have some deformation starting to form in this area. You can visualize that like it just showed in the wind field. So now that you know your deformation is there, you have a temperature gradient in place, so you're going to get frontogenesis because your deformation is acting on that temperature gradient. So here's the frontogenesis. It's kind of weak, but you still have really good warm air advection. We're assuming it's saturated in here. So you have weak frontogenesis. It's just starting to get going. Weak deformation. So at 7 p.m. on the 11th, what would your radar, like as far as banding goes, look like by that point? There probably really won't be that much of a band there. And here's the radar image. It's just starting to get going. You just have a broad, a lot of moderate snow in here, but there's no really well-defined bands yet. So let's go ahead. 6 hours later, at 1 a.m., your mid-level low starting to tighten up. And here's your temperature gradient is really tightened from before. You're only -3 at 700 down well south of Long Island, and you're like -16 up here towards Binghamton. And you can see that temperature gradient really getting going in your cross isobar flow. Look at that 45 knots of wind here south of Long Island from the due south across that gradient, but only like 10 to 15 knots over Connecticut. So that air mass is really starting to converge. So here's the deformation. It's really starting to strengthen now with the axis basically from Philly up just south of Long Island. It's getting a lot stronger. So since your deformation is strengthening over a temperature gradient, you're going to have strengthening frontogenesis. And you can see how the frontogenesis is definitely stronger, and it's really starting to tighten up right over Long Island there. So we'll take a look at the radar at 1 a.m. And you do have a lot of overrunning precip, but you're starting to see areas of banding start to take shape, especially across southeast PA, maybe across some of Connecticut, but this is the area we really want to focus on.